Imagine you're a scientist and you've just run the most important experiment of your life. You have your data in hand and it supports your hypothesis. You can start dreaming of that Nobel Prize. Or can you? Did you remember to run a significance test? We can't always take our data at face value. We need to run statistical tests to make sure that the trends we're seeing aren't due to randomness. Luckily, mathematicians have our backs and have developed standard tests we can run on our results to ensure that our data check out. As a researcher, chances are that you'll frequently use the chi-square test, which assesses whether the results of an experiment are statistically significant. Chi-square tests come in a few different flavors. Today we'll be doing the chi-square test of independence. If you want to try another flavor, we've put a link in the description to a method video that walks through an example of the chi-square goodness of fit test. A chi-square test of independence assesses whether there is a statistically significant relationship between two variables in an experiment. To show how this works, I'm going to evaluate some data that I collected from these onion root microscope slides. For my experiment, I want to determine if there is a relationship between the location of the cell in the root and which phase of the cell cycle a cell is in. I looked at cells in two different locations on the root, right at the tip and the area above the tip, which is known as the elongation zone. So location is my first variable. At both locations, I counted the number of cells undergoing mitosis, also known as M phase, and which cells were in interphase. So the cell cycle phase is my second variable. Let's review my data laid out in a table. My column categories are the two locations, root tip and elongation zone. And the row categories are the two cell cycle phases, M phase and interphase. In the root tip, I have 12 M phase cells and 71 interphase cells. In the elongation zone, I have 2 M phase cells and 82 interphase cells. At first glance, it looks like location and cell cycle phase could be correlated. There are more mitotic cells in the tip than in the elongation zone. But we won't know for sure if this seeming relationship is just due to randomness unless we do our chi-square test of independence. Before we begin, we need to introduce an important component of the chi-square analysis, the null hypothesis. A null hypothesis states that there is no significant difference between the groups or variables that are being tested. So the null hypothesis for our specific chi-square analysis is there is no relationship between location and cell cycle phase. In other words, location and cell cycle phase are independent. The chi-square test of independence assesses whether there is a significant difference between our data, in other words, the observed outcomes of our experiment, and the expected outcome if our null hypothesis were true. In my case, this data table represents my observed outcomes. Now we have to figure out what the expected outcomes of the experiment would be if there were no relationship between location and cell cycle phase. To do this, first I'm going to calculate the column and row totals for my data table by adding up the data values in a given column or row. The total of my M phase row is 14, and the total of my interphase row is 153. The total of my root tip column is 83, and the total of my elongation zone column is 84. Adding up either the column totals or row totals should give me the same number. Let's call it the grand total. In this case, the grand total is 167. In a chi-square test of independence, calculating the expected value for a given combination of variables goes like this. We take the corresponding column total, multiply it by the corresponding row total, and then divide by the grand total. So for M phase root tips, the expected value would be 14 multiplied by 83, then divided by 167, which is 6.96. Rounded to the nearest whole number, that's 7. Let's do the same for all other combinations and fill out a new table of expected values. Our expected value for elongation zone M phase is also 7. For root tip interphase, it's 76, and for elongation zone interphase, it's 77. Now we can use our observed and expected values to calculate our chi-squared value, which is the difference between the observed outcomes of the experiment and the expected outcomes if the null hypothesis were true. Written as an equation, that would be chi-squared equals the sum of the observed outcome minus the expected outcome squared, then divided by the expected outcome. In other words, we will be performing that operation for each variable combination in our table, and then adding the resulting values together to get the final chi-squared value. Let's make another table to keep track of it all. with observed and expected values for each pair of variables. Below, we'll add some rows for each step of the chi-squared calculation so that we can fill them in as we go through all the variable pairs. Note that observed is abbreviated to O and expected is abbreviated to E. Let's walk through the calculation for the root tip M phase pair. My observed value is 12, my expected value is 7. So observed minus expected is 12 minus 7, which is 5. 5 squared is 25, divided by 7 is 3.6. If we do that for the other pairs, we get 0.3 for root tip interphase, 3.6 for elongation zone M phase, and 0.3 for elongation zone interphase. Our chi-squared value is the sum of all of these numbers, 7.8. But what does it mean? In order to know whether our chi-squared value is high enough to reject the null hypothesis that there is no relationship between location and cell cycle phase, we need to determine two more values. The first is how confident we want to be in our determination of statistical significance. Scientists commonly use a p-value of 0.05, so let's go with that. This means that we want to be 95% certain that our results are legit and not due to random chance. The second value we need to determine is the degrees of freedom in our experimental setup, which is the number of values in our data table that are actually independent. In other words, it's the number of cells in the grid you have to fill in before you can figure out the rest based on the row and column totals. To find this degrees of freedom value in a chi-square test of independence, you simply take the number of rows in our data table minus 1 and multiply it by the number of columns in our data table minus 1. We had 2 rows and 2 columns, so that's 2 minus 1 times 2 minus 1, which is 1 times 1, which is just 1 degree of freedom. Now we're ready to consult our handy-dandy critical values chart, which is a standardized list of chi-squared values that are needed to reject the null hypothesis for a given degree of freedom and confidence level. From the chart, I can see that for 1 degree of freedom, I need a chi-squared value of at least 3.84 in order for me to be 95% certain that my data rejects the null hypothesis. My chi-squared value is 7.8, which is greater than 3.84. So I can reject the null hypothesis that my two variables are unrelated. Woohoo! While this test tells me that there is a relationship between cell cycle phase and location in the root, it can't tell me whether one variable causes the other. Remember, correlation doesn't necessarily equal causation. We would need to do some more experiments to figure that out. Now you're ready to go off and perform a chi-square test of independence on your own data. And I'm ready to go collect my Nobel in onion root tip cell division dynamics. See you in Stockholm!